Question number one, we already know that triangle ABE and triangle CDF are congruent to each other. If we know that the triangles are congruent, then we can CPCTC some information like AB congruent to CD. We can also CPCTC angles BAE and angles CDE being congruent to each other because those are corresponding angles in the two congruent triangles. And since these are alternate interior angles, you can see the letter Z over here. If we have congruent alternate interior angles, that proves that the lines forming them are parallel to each other. So here what we have is one pair of opposite sides that are both parallel and congruent to each other. So from there, we can conclude that we have a parallelogram because that's one of our methods of proving that we have a parallelogram, showing that one pair of opposite sides is both parallel and congruent. In order to prove that I have a rectangle, I would have to prove a rectangle property. In order to prove I have a rhombus, I would have to prove a rhombus property. And in order to prove a square, I would have to prove a property from both a rectangle and a rhombus. I'm not seeing how else I can get any more information here because all that I was starting with was the fact that these two triangles are congruent to each other. So I can't really get information about these two triangles because there's nothing additional given to us. I think this is as far as I can get in this question. So I'm going to go with answer choice number 4, a parallelogram. One pair of opposite sides is both parallel and congruent, proving that we have a regular parallelogram. Quadrilateral best. Let me draw quadrilateral best. Anytime you have a question and they talk about something but they don't give a picture, draw your own picture. And it has diagonals that intersect at point D. And we're seeing which answer choice is not sufficient to prove that we have a parallelogram. So that means 3 of these answer choices are going to prove it's a parallelogram, and we're looking for the one that won't. So let's try out each of the answer choices. Answer choice 1. BD is congruent to SD, and ED is congruent to DT. This does prove it's a parallelogram because this is the property that diagonals bisect each other. In answer choice 2, we have BE congruent to ST and ES congruent to TB. This does prove it's a parallelogram. This is both pairs of opposite sides congruent to each other. In answer choice 3, we have ES congruent to TB and BE parallel to TS. This does not prove that we have a parallelogram because it's either both pairs of opposite sides congruent or both pairs of opposite sides parallel or one pair of opposite sides that is both parallel and congruent, not one pair of sides that is congruent and a different pair of opposite sides that are parallel. That is not a property of a parallelogram. This one here is supposed to have parallel symbols over here. This does prove that we have a parallelogram in answer choice 4 because that would be both pairs of opposite sides parallel to each other. In answer choice 3, In answer choice 3, we are looking for the measurement of this angle over here. Now, we have a rhombus and we know one of the angle measurements. And some properties of rhombuses are that all the sides are equal, but that's not really going to help us here because we're dealing with angles in the question. Diagonals are perpendicular. So that means where the diagonals intersect, they form 90-degree angles. Oops, that was supposed to be a 90-degree angle. It's hard to draw this. And that's really all I need for this question. Because if I know that this is 90, and I know that this is 12, I know that all 3 angles in any triangle need to make 180 degrees. So I can find the missing angle by seeing what it needs to be in order to make 180 degrees. Let me get my calculator out. So I have 90 plus 12, that is 102. 180 minus 102 is 78 degrees. So the angle that we're looking for, this angle right over here, is 78 degrees. Moving on to number 4, we have an isosceles trapezoid, and I know a bunch of things about isosceles trapezoids. Number 1, they're regular trapezoids, so we have that their bases are parallel to each other. Specifically, since it's an isosceles trapezoid, I also know that the legs are congruent. I don't really think that's going to be helpful here because we have information about the angles in the question, but just so we remember that's a property of isosceles trapezoids. And we also know that the base angles are congruent to each other. So the lower base angles are congruent and the upper base angles are congruent to each other as well. Now, in order to figure out what the x value is, we need to get the connection between the angles up here and the angles down here. Since we have parallel sides, we have parallel lines cut by a transversal. So the upper base angle and the lower base angle directly below it are same side interior angles. They're inside the parallel lines on the same side of the transversal. So they do need to make 180 degrees. And then since these are congruent, I can just represent this one as 3x plus 5 because both of the lower base angles are congruent to each other. So 2x, that angle, and the 3x plus 5 angle directly below it together need to make 180 degrees. Once again, that's because they are same side interior angles, and same side interior angles are supplementary when parallel lines are cut by a transversal. Here I have 5x plus 5 is equal to 180. That is 5x is equal to 175 degrees. In order to get x by itself, all we need to do is 175 divided by 5, and I get 35 for our x value. The question's asking to find the measure of angle BAD, so that's this angle right here. So if I do 35 times 2, that gives me 70 degrees for this angle. And I know it doesn't say to fill in the rest of the measurements, but since the upper base angles are congruent in an isosceles trapezoid, these would be 70. And since the upper base angle and the lower base angle directly below it are supplementary, these two angles would be 110 degrees. Once again, it was just asking for angle BAD in the question. Number 5, it's asking in this question which answer choice is enough, is sufficient to prove that we have a parallelogram. So 3 of the answer choices are not going to be enough. There's only going to be one that gives us enough information to prove that the quadrilateral is a parallelogram. We're going to try out the different answer choices in the diagram. So the first one says angle 1 is congruent to angle 6, and that angle 9 is congruent to angle 14. Well, those are vertical angles, and vertical angles are always congruent. They don't help us prove any of the special properties of parallelograms. If they were a different kind of angle, maybe they could help us prove that we had parallel lines or something of that sort. But unfortunately, this is not going to be enough. Okay, number 2. Angle 5 is congruent to angle 10, and angle 6, let me use a different color for this, is congruent to angle 9. So these are alternate interior angles in the corner of the Z over here. So that proves that lines L and M are parallel. And then we have our other set of alternate interior angles, but they're also formed by the same lines L and M. So here, since both of those sets of alternate interior angles are formed by lines L and M, all we have information here to show is that L is parallel to M. We don't have information about the other set of sides being parallel. So this is not enough to prove that we have a parallelogram, but we're getting closer. Answer choice 3. Angle 5 is congruent to angle 7, and angle 10 is congruent to angle 15. Let's take a look over here. So angle 5 and angle 7 are corresponding angles. They're both top left, where the lines are cut by the pencil. And if corresponding angles are congruent, the lines forming them are in fact parallel to each other. So this would prove that the lines forming those corresponding angles, N and P, are parallel to each other. So I'm going to put that over here. on the actual parallelogram. And in P, those lines are parallel to each other. So right now we have one pair of opposite sides that are parallel to each other from the congruent corresponding angles. Now let's check out the other pair of angles that they gave us. So here's angle 15. It's vertical to angle 12. Vertical angles are always congruent. And angle 10 and angle 12 are also corresponding angles, bottom right, bottom right. So once again, when corresponding angles are congruent, the lines forming them are parallel. But here, the lines forming them are once again N and P. So this just proved again that N and P are parallel, but we still don't know that the other set of sides, L and M, are parallel to each other as well. So this is not going to be the answer choice that we are looking for. Finally, angle 6 congruent to angle 9, and angle 9 congruent to angle 11. So let's start off with angle 6 and angle 9. So angle 6 and angle 9 are alternate interior angles. And when alternate interior angles are congruent, the lines forming them, which are M and L, are parallel to each other. Now let's take a look at 9 and 11. They are corresponding angles, top right, top right. And when corresponding angles are congruent, the lines forming them are also parallel. So that would be P and N. So this does give us the information that we need because we had these opposite sides parallel from the alternate interior angle 6 and 9. And then we had these opposite sides parallel from the corresponding angles 9 and 11. So this is the answer choice that we are looking for. Question number 6. Which set of statements would describe a parallelogram that can always be classified as a rhombus? So I'm going to draw a picture of a rhombus and not drawn to scale, but I'm just going to mark as many rhombus properties as I can remember. So rhombuses have 4 equal sides. So not only are opposite sides congruent, but all 4 sides are congruent as well. That's a special property of a rhombus. The diagonals are perpendicular to each other. So that means that they make 90-degree angles where they intersect. And the diagonals bisect the angles. Remember, since it's also a parallelogram, the opposite angles are congruent and they're getting bisected because in a rhombus, diagonals bisect the angles. And once again, opposite angles are congruent because it does have parallelogram properties. And the diagonals are bisecting the angles as well. So there we go with that. And remember, a rhombus, since it does have all of the parallelogram properties, it does have diagonals that bisect each other because that is a parallelogram property that also applies to a rhombus. We have a lot of stuff marked using all the properties of rhombuses and parallelograms that we could remember. So let's take a look at the answer choices now. Diagonals are perpendicular bisectors of each other. They are. They form 90-degree angles, that's the perpendicular part, and they each split each other in half. So they are bisectors of each other. So answer choice 1 is correct. So I'm going to knock out 3 because that doesn't include answer choice 1. Number 2, diagonals bisect the angles from which they are drawn. Yeah, that's a special property of a rhombus. Diagonals are angle bisectors in a rhombus. So that one's good to go. I'm going to knock down answer 2 because that doesn't include 2. And finally, number 3, diagonals form 4 congruent isosceles right triangles. Although they do form right triangles that are congruent to each other, these are not isosceles triangles. And maybe it was weird the way I marked it. So I marked the equal sides first, and then I was marking that diagonals bisect each other. So these are being split in half, and these are being split in half. See that we don't have isosceles triangles. And the reason that we don't have isosceles triangles is because the diagonals just bisect each other, but the diagonals are not congruent. It's a rectangle that would have congruent isosceles triangles. They wouldn't be right triangles, but a rectangle has congruent diagonals, and they're also bisecting each other. A rectangle would have the isosceles triangles, but it wouldn't have the right angles by the diagonals, so they wouldn't be the right triangles. So no, if it didn't have the isosceles part, it would be good, but they don't form isosceles triangles. They just form congruent right triangles, but they're not isosceles. So that would be answer choice 1, 1, and 2. Okay, number 7. So over here we have AC, which is the length of this entire diagonal is 18. And we have BD, which is the length of the other entire diagonal of this rhombus is 24. But remember, a rhombus has all the properties of a parallelogram. So I know that the diagonals bisect each other, which means that they're being split, each of them, into 2 equal parts. So instead of writing 18 and 24, I'm going to write what each half is. Each half of AC would be 9. So we have 9 and 9 to make the 18. And each half of BD would be 12. That's 12 and 12 to make the 24. And what we're looking for is the length of one side of the rhombus. So I'm just going to focus in on one of these triangles because they are all the same. And the other key that we're going to need here, since we are talking about the diagonals of a rhombus, is that the diagonals are perpendicular to each other. So that means they form 90-degree angles where they intersect. Here are 4 right triangles. And as I mentioned before, I just focused on one of the right triangles because they are all the same. We have 2 sides of this right triangle. We have 9 and we have 12. And what we need to do is find the missing side. When we need to find the side of a right triangle, the missing side, and we already have 2 other sides, that's the Pythagorean theorem that we're going to use. Remember, the Pythagorean theorem is a squared plus b squared equals to c squared, and c needs to go into the hypotenuse. C needs to be the hypotenuse. So if I look opposite from the 90-degree angle, I'll find the hypotenuse. So the hypotenuse is actually the missing side here of the rhombus that we are looking for. So I'm going to leave that as C because we're solving for the hypotenuse here. And our 2 legs are 9 and 12. So that is 81 and 144. And now I just need to add the 2 together. Let me get my calculator out. 81 plus 144 is 225. And that is a perfect square. So when I take the square root of both sides, I get C is equal to 15. So one side of the rhombus is 15. If you wanted to find all the sides, if you wanted to find the perimeter, you would just add 15 up for all 4 of the sides, since all the sides of a rhombus are in fact equal to each other. So the perimeter of this rhombus, if the question did ask for it, would be 60. 15, 60. Moving along to the next one. We have a rectangular gate with 2 diagonal supports. Angle 1 is 42 degrees. What is the measure of angle 2? So since we have a rectangle here, we have to think about our rectangle properties. Rectangles have 90-degree angles, and that might be helpful here because we are talking about the angles of the rectangle. Another thing that we can remember is the diagonals of a rectangle are equal. And since a rectangle is also a parallelogram, the diagonals also bisect each other. Since the diagonals are equal and they bisect each other, each of the pieces are going to be the same. For example, if this diagonal is 10 and this one's also 10, then each of these has to be 5 because the diagonals are congruent and they're each being split equally. So what we have here are a bunch of isosceles triangles, so that might help as well. First, I'm going to find this angle over here because we already have the 42 and we know this whole angle is 90 degrees. So I'm going to do 90 minus 42 to find that missing piece of the right angle. And I have 48 degrees. I also want to keep in mind since the rectangle is a parallelogram, the opposite sides are in fact parallel to each other. And I actually do have a letter Z here. I do have alternate interior angles. So this 42-degree angle is alternate interior with this angle over here, so that also needs to be 42 degrees. This helps me out because now I am down here in the triangle that I am interested in finding the angle of. And I know this is an isosceles triangle. And not only do isosceles triangles have two equal sides, they also have two equal angles. And those equal angles are located opposite equal sides. That is the base angle theorem. If a triangle has two equal sides, the angles opposite those sides are also equal. So across is the 42. Across, this one is also 42 degrees. Remember that all angles of any triangle need to add to 180 degrees. So now that we have the two 42-degree angles of this blue triangle, all we need to do is find the missing angle to make 180 degrees. So I'm going to add up on my calculator 42 plus 42, and that's 84. I'm going to do 180 minus 84, and I get 96. So I'm going to put that over here. This missing angle is 96 degrees. There we go, and that's the measurement of angle 2. Moving on to number 9, we have a rhombus here, and it has diagonals, and we need to find a bunch of different things. First, we're going to start off with finding SR. When I take a look at SR, that is a side of the rhombus, and it has an expression that uses the variable x. Right now, I'm going to try to set up the equation to solve for x, and then I can take my x value and find the length of SR. Now, since it's on the side of the rhombus, I'm going to think about my rhombus properties sides. And I know that all sides of a rhombus are equal. You can also think of it as consecutive sides are equal because we do have two consecutive sides on our rhombus with measurements on it. But all sides of a rhombus are equal, consecutive sides are equal. That implies that all sides are equal. So I'm going to set up the equation 8x minus 5 is equal to 3x plus 30. From here, I'm going to subtract 3x from both sides, and I'm going to add 5 to both sides, and I have x is equal to 7. Now I'm just going to plug in to 8x minus 5 to find the length of SR. So 8 times 7, that is 56, minus 5 is 51. So the length of SR is 51 degree. 51, not degrees. This is not an angle. My bad. Moving along. Now we're going to find the measurement of RT. So taking a look, RT is one whole diagonal of this rhombus. So I'm going to start thinking about some diagonal properties. I do know that diagonals of a rhombus follow the same parallelogram property. Diagonals bisect each other. And I know that on this other diagonal, SA, it also uses the same variable z as it used on RT. And we have both of the pieces. So since I know that both pieces of this diagonal are equal to each other, I'm going to take the equation that says c is equal to 4z minus 8. Once again, that's because diagonals of a rhombus bisect each other because they do also have all of the parallelogram properties. Okay, I'm going to subtract 4z from both sides. I have negative z equals to negative 8. I'm going to divide both sides by negative 1, and I have z is equal to 8. Now I'm just going to take my z value and I'm going to plug in. So I'm going to do 5z plus 5. So that is 8 times 5, which is 40, plus 5 is 45. And then since the diagonals bisect each other, this half of that diagonal RT should also be the same. And then adding them up together, 45 plus 45 is 90. So I'm going to write that here. RT is 90. That is the total length of diagonal RT. It is 90. SA will not be the same length because this is not a rectangle, so the diagonals are not congruent to each other. Okay, now we're going to find the measure of angle TAS. So angle TAS is this angle right over here represented as 9y plus 8. So what we need to do now is we need to figure out the value of y, and then we can plug in and find the measure of angle TAS. I'm going to think about if there's any other properties of rhombuses that I remember that can help me get some more angle measurements here to work with. And I remember that diagonals of a rhombus are perpendicular to each other. So these are all 90-degree angles over here. And that helps me out because this angle, the 9y plus 8 angle, is inside this triangle over here. Always look out for triangles. In this triangle, we have this angle, 9y plus 8. We have this angle, 5y minus 2, and now we have a 90-degree angle. So we have information about all three of these angles. we know what all three of the angles have to add up to. In any triangle, all three angles must always add up to 180 degrees. Let's make an equation to find that. 9y plus 8 plus 5y minus 2 plus 90 equals to 180 degrees. Now I'm just going to combine all of my like terms. That is 14y. 90 minus 2 is 88 plus 8 is 96. Now I'm going to do 180 minus 96 now that I've combined my like terms. And I have 14y is equal to 84. Let's hope that divides evenly by 14, and it does. Y is equal to 6. Now that I have my y value, I can just plug in for angle TAS, which is what I'm solving for, 9y plus 8. So 9 times 6 is 54 plus 8 is 62. So I'm going to write that over here. That is 62 degrees because it is an angle. So the measure of angle TAS is 68. Oh, sorry, 62 degrees. I wrote 62 over here. Then I was trying to write 68 over here for some reason. 62 degrees. Okay, now we are up to the proof questions. So over here in this question, we have a rhombus. So we know a lot of properties about quadrilateral PROE because we know a lot of stuff about rhombuses. And we're also given that angle SPR, that's this whole angle over here, is congruent to angle VOR. And our goal is to prove SE congruent to EV. Now, SE is a side of this triangle over here, and EV is a side of this triangle over here. So our goal is going to be to prove those two triangles congruent, because if we prove those two triangles congruent, then we can just see PCDC sides SE and EV. So let's think about how we can get some information in those two triangles. So already we were given angle SPR, this angle, and angle VOR, this whole angle. But this angle is larger than what's inside the two triangles. I want to use subtraction. But remember, in order to use subtraction, not only do you have to start with congruent angles, but you also need to be subtracting congruent angles. So for example, if I wanted to take this angle and subtract off this to be left over with this, and I wanted to take this angle and subtract off this to be left over with this, I would need to know that these two are congruent in order to subtract from the big angles. And luckily, since I do have a rhombus here, I do know that these are congruent to each other because they are opposite angles of the rhombus. Remember, rhombuses have all of the same properties as regular parallelograms, including the fact that opposite angles are congruent to each other. So now, if I state first that these are congruent to each other, then I can subtract. I can do this red angle minus the blue angle to give me this angle that I want inside the triangle. And I can do this red angle minus the blue angle to give me this angle that I want inside the triangle. And now I'm getting closer. I also know that all sides of a rhombus are equal. Or you can also say consecutive sides are congruent, because the two sides that we do need are ones that are consecutive to each other. But all sides of a rhombus are congruent. Consecutive sides are congruent as well. You can say it either way, and that is the same thing as each other. And the last thing that we need, let me just move this away to see if I'm right. Yes, we have a letter X there. Let me highlight the letter X formed by the intersecting lines. What we have are our congruent vertical angles. I'm going to put that here and here. And now we can prove the angle is congruent with ASA. Then it will be one more step of our proof to CPCTC the sides that we need. So I'm going to write up this proof. Please try to also write up the proof yourself if you haven't already. Try to take all of the components that we talked about together in making our plan and put them into your proof. And remember that planning your proof is very, very important. A lot of you guys on the Delta Math have like 35 steps that are unnecessary and don't lead you to achieving your goal. If you think about what your goal is and what you have and what you can conclude, and you mark your diagram first and try to come up with a plan, then you'll avoid putting 65 unnecessary things into your proof that don't need to be there. Here's the proof written up. Just make sure that you have everything that is here in your own proof as well. Moving on to the next one. Feel free to pause the video if you need it. For the next one, we're told that ABCD is a square. So we know a lot of stuff about it because it's got all the parallelogram properties, rhombus, and rectangle properties if it's a square. We're also told that AE is congruent to AF, so I'm going to mark that in the diagram as well. And the first thing that we need to prove is that triangle BAF is congruent to triangle DAE. So aside from the given sides, I also see that there are vertical angles here. We have that letter X formed by the intersecting line, so we do have congruent vertical angles. And since we have a square, it does have the rhombus property that all sides are equal to each other. So I do know that sides BA and AD are congruent to each other because all sides of the square are congruent. And that gives me that triangle BAF is congruent to triangle DAE by SAS. I'm going to pause the video and I'm going to write this part up so far, and then we will move on to part B. The next part of this proof is we need to prove that angle CBF, so angle CBF is this whole angle over here. So it includes the angle that's in the square, but also this piece outside of it that's part of the triangle, is congruent to angle CDE. So angle CDE is this whole angle here. So that includes the angle that's part of the square and also this little piece of the angle from the triangle. We just proved the triangle's congruent, so we can say that these two angles that they just marked in red are congruent to the CPCTC because they are corresponding sides of the two congruent triangles. And since we know we have a square, we know that it does have all of the properties of a rectangle as well and a rhombus. So we know that all of the angles are right angles, and right angles are always congruent to each other. So with addition, what we can do is we can add up the red and the blue to make the whole black angle that we need. And here we can add up the red and the blue to make the whole black angle that we need. So I'm going to pause the video and write this up. And here we have the proof fully written up. I ran out of space over here, so steps 7 and 8, where I actually do the addition and the substitution, are over here on the right side of the page. Feel free to pause the video so that way you can see that you have the same thing on your own paper. Oh, it looks like the diagram went missing. Let me grab that diagram. And let me move that back over here. Okay, perfect. So here we have a rectangle, and what they also give us to work with is that angle ADG, which is this angle over here, is congruent to angle BCG, which is this angle over here. And ultimately, our goal is to prove that AE is congruent to BF. Now, I'm just noticing that AE is a piece of AF, and AF is a side of this triangle over here. And I'm also noticing that BF is a piece of this side BE, which is a side of this triangle BCE. I'm thinking that if we can prove these two triangles congruent, then we can get closer to our goal of showing that AE is congruent to BF. So I'm going to see what else I can get about these triangles to prove them congruent. So that way I can get to the sides that I need up here that are going to help me out. Since I have a square, I know that all the sides of a square are equal. So I know that this side and this side, sorry, a rectangle. I know that opposite sides of a rectangle are equal. My bad. So AD and BC are congruent. They are opposite sides of the rectangle. And since we have a rectangle, I do know all of the corner angles are 90-degree angles. So I know that angle A and angle B are 90-degree angles. So now I know the two triangles are congruent by ASA. Once I know the triangles are congruent by ASA, I can CPCTC this side over here, AF, and I can CPCTC that side over there, BE. And if you're wondering why we're going to do this, if I draw the triangle separately, it might make a little bit more sense why this is happening. So this is BEC, and this is AFD. So if we prove these two triangles congruent, because right now we have enough information to do that with ASA. If we prove the two triangles congruent, then we can CP/CTC these two sides. And then once we have the full sides, then we can subtract off EF, and we can just get the pieces of those sides, AE and BF, that we need. So I'm going to write up this whole thing. When you do the subtraction, you do need to state that FE is congruent to itself, because you are going to be doing AF minus FE to get AE, and you are going to be doing BE minus EF to get BF. So since you're going to be subtracting FE off of both of the larger segments, remember you have to start with congruent and also subtract congruent. You're going to pause the video and hit the proof. Try to do it yourself as well. And here is this proof written up. Moving on to the next one, number 13. So what we need to do is prove that we have a trapezoid, but that the trapezoid is not isosceles. Here I have the proof completely written up. In order to prove it's a trapezoid, we have to show that one pair of sides is parallel. So here I have the work for that, as well as a concluding statement explaining why it's a trapezoid. And then to show it was not isosceles, I showed that the legs, KE and AT, were not congruent. So I found that with the distance formula to show the lengths were not the same. And then I put a concluding statement explaining what I proved. It's not isosceles because its legs are not congruent. Moving down to the next one over here, Jim created a quadrilateral, and he believes that he has created a rhombus but not a square. So in order to be a rhombus, remember first it needs to be a parallelogram. It never says anywhere here that it's a parallelogram. So the very first thing I would need to do is prove that it's a parallelogram. And then I would need to prove that it's a rhombus by proving a rhombus property. And finally, I would need to prove a rectangle property, which will not end up being true because it's not supposed to be a square. So I'm just going to go with one method. There are multiple different approaches, but I'm just going to do one method of this. So in order to prove that I have a parallelogram, I chose to use distance formula for all four sides to show that both pairs of opposite sides were congruent, making it a parallelogram. And then since I already had all the side lengths, I also see that the sides are all congruent to each other. So I knew it was a rhombus because it was a parallelogram with four equal sides. And then in order to see if it was a rectangle, I actually found the length of the diagonals, which should be congruent if it is a rectangle. And when I did my distance formulas for the two diagonals, they did not turn out to be congruent to each other. So I did not have a rectangle here.